Student gets into solubility, spectroscopy, and finally Beer-Lambert's law. So we're going to roll through these. It takes the information that we've talked about in the previous videos and kind of brings them all together and shows you how we use them experimentally. So what is solubility? We're going to talk about whether things are capable of being soluble, so they're able to mix together and form a solution. And we've already kind of touched on this when we were talking about polar and nonpolar and why they dissolve in one another. But we're going to continue kind of talking about that here. So solubility in solvents. Intermolecular forces of the substances are similar. They tend to be miscible. So this is a common term that you'll see, this miscibility. So they're going to mix together. Ionic substances with polar substances will mix together because their charges will be attracted. Nonpolar substances dissolve in nonpolar substances because they don't have any of those charges kind of holding things either together or allowing them to mix. Do not use like dissolves light. You cannot use that on the test. They will mark it wrong. You have to explain it in terms of polarity. So in order for any solute to dissolve in a solvent, the solute and solvent attractions must be broken, both of them, and then the solvent and solute attractions have to be made. So in this combination of factors that determines the solute will dissolve, you have to look at those polarities and see if it's polar. If things are polar and they're dealing with ions, it's going to dissolve. If you're dealing with two nonpolars, then they will dissolve. So make sure that you're paying particular attention to that and do not use like dissolves like. All right, so pause the video and see if you can come up with the answers to these two questions. And here's a couple more, so see how you do with those. And then we'll go through the answers. All right, so the first one, the LDFs were approximately the same, but the IMFs that dramatically increase the attractions between the molecules of the alcohol are going to come into play. So when we look at this guy, because this oxygen has lone pairs of electrons, a hydrogen's attached, we're going to have hydrogen bonding here. And so because of that, that's going to dramatically increase the boiling point of the butanol versus the pentane. And then because the LDFs are the same, there has to be something else at play. So then we were looking at this one. The boiling point of HCl is minus 85 and chlorine is minus 34. Why is that? Well, if you look at the masses of these, now this guy is going to be polar. And so you would think just from the polarity aspect that this guy being polar, he would end up having a higher boiling point than the chlorine. But the chlorine has stronger LDFs because there's a lot more electrons going on here. So when we look at that in terms of the boiling points, we're able to see that the HCl actually has a lower boiling point than the Cl2, and it's because of those LDFs that create that. And then we had 3 here. Noble gases are made up of monatomic particles. What would you expect the pattern of boiling points for the elements to be as you go down 18? So we're going to increase those boiling points because the LDFs are going to increase, and we're also increasing the surface area. Okay, then we talked about, we've briefly touched on vapor pressure as well. So liquid sealed container, liquid is below its boiling point, but we're going to have some of those molecules go up into vapor and some of them will go back down into liquid, and it keeps this kind of keeps moving back and forth, and it's just keeps transitioning. But things with weaker intermolecular forces are going to have relatively high vapor pressures because it's easier for those molecules to escape that liquid state and go up into the gaseous state. So remember that if a thing has a relatively high vapor pressure, we call, and they have weak intermolecular forces which cause this vapor phase to go in to have, cause it to happen. That then gives the term here for this being a volatile substance, okay? And remember, volatility isn't the same as flammability. They tend to go hand in hand, but they don't always have to. All right, so let's look at some spectroscopy and how that works with this whole unit. Okay. We're also going to look at something called Beer-Lambert. So spectroscopy we looked at before when we were back in Unit 1. And we look at the electromagnetic radiation and matter. We look at what wavelengths are being given off and reflected. And depending on that type of radiation, we're able to accumulate some data about that. So we saw back with our PES, our photoelectron spectroscopy, that UV and visible lights tend to cause these electronic transitions, and we're able to gather information about those electron configurations from that. So when we have these covalent bonds and they're exposed to these infrared radiation, that's going to cause them to vibrate. So infrared, vibrate. And we're able to distinguish different compounds based on that. Microwaves will cause molecular rotation. And the way that I remember that microwaves or the molecular rotation is that in a microwave, you often have that turntable that goes around or rotates. So microwaves both start with M, so molecular, and then rotation because of the turntable. So they're going to cause the composition to change under that test. We can measure the photons that are of the light that's being given off, and the radiation. I guess it doesn't necessarily have to be light. And if you remember back, we used these equations where we had the speed of light equals the wavelength times the frequency. And then we also had energy equals Planck's constant times frequency. So we spent quite a bit of time in first year chemistry on these equations. And we can also, when we do this, remember that we're oftentimes working with times 10 to the situations. And on the multiple choice exam, and historically in the past, you've never been able to use a calculator. So you need to know how those superscripts work. So if we're dividing, for example, we would take this and we would go and we would add, when we're multiplying, we add these together. When we're dividing, we subtract the coefficients. So keep that in mind when you are when you're trying to work with some of the math in this. You have to remember your metrics too. Okay, giga, mega, kilo, these are all going to come into play. We also have nano that we're going to get into, and micro. So you've got to get these conversion factors memorized as well. A couple of these problems. So the first one, we have 422 nanometers. We're trying to figure of a wavelength. We're trying to figure out the frequency. And the first thing that we need to do is we need to change this number over into meters. And the reason why we have to do that is because we're going to use the speed of light here. The speed of light is 3.0 times 10 to the 8th meters per second. And so we have to change this over into meters in order for this constant to work. So 422 nanometers. And I know that if I had 1 times 10 to the 9th nanometers, I would have 1 meter. And I got that from the conversion factors here. This is just working it the opposite way. If I make this 1 and make that, or if I make that 1, I would have 1 times 10 to the 9th. So that's where I get that. So I'm going to convert that over and grab my calculator here. And that ends up being 4.22 times 10 to the negative 7th. So if I have this and I have this, remember C equals wavelength times frequency. So if I'm solving for frequency, I can do that. I can do my frequency here equals my speed of light over my wavelength. And then I just need to substitute in my values. So the speed of light is up here. And that's going to be meters per second. And then I will put in this value for my wavelength, and that's going to be 4.22 times 10 to the minus 7, and that's going to be meters. So then my units will cancel. I can get my meters to cancel here. That's going to leave me with a value of 1 over seconds. And remember, 1 over seconds equals hertz. So then we just need to plug this information into our calculator. And our answer comes back to us. We want 2 significant figures, or 3 significant figures, because this is 3 sig figs. And this is going to be 7.11 times 10 to the 14th. And you can either put 1 over seconds or you could say hertz. Then they're asking us what the energy is going to be from this light. So energy equals Planck's constant times our frequency from up here. I'm going to do Planck's constant in green so you can see the units that are going to cancel out here. Now that's probably not the best. Let's try red. We'll just try every color. We'll make it a rainbow. All right, so when we go through this, we're going to have our energy equals our Planck's constant, which is 6.626 times 10 to the negative 34. And that is joules seconds. And then we are going to multiply that times our frequency, which is here. We're going to grab that value and bring it down. And that's going to be 7.11 times 10 to the 14th. And if we leave it as 1 over seconds, then our seconds would come down here. And what ends up happening then is we end up being able to cancel our units out. So these seconds go away, and that leaves us with energy in joules, which makes sense because that's what energy is measured in. So we're going to take our frequency and multiply it by Planck's constant. And we end up with, and we want to have 3 sig figs in our answer. That's going to be 4.71 times 10 to the negative 19th, and that's going to be joules. All right, here we have another practice problem, so you can pause the video and practice this one as well. And again, this is very common that you're going to have to change out of nanometers and get that into meters. So 680, and that's going to be nanometers. And my nanometers, in 1 meter, I have 1 times 10 to the 9th nanometers. And when I pull that through, I end up with 6.8 times 10 to the negative 7th nanometers. We're solving for frequency. So frequency is going to equal the speed of light over the wavelength. And then I'm going to put the wavelength down here. Oops, that shouldn't have been nanometers. That should have been meters up there. Sorry, my nanometers had canceled. There we go. So 6.8 times 10 to the minus 7, and that's meters. So then my meters cancel here. That leaves us with 1/seconds, which is hertz. And my calculator brings me to 4.4 times 10 to the 14th, and this is 2 sig figs because this is a 2 sig fig number. There is no decimal after the 0 here, so that 0 is not significant, so that gives us a 2 sig fig for our answer. All right, here we have wavelength given in meters, or they're asking us to solve in meters. We're given the frequency. So here we have kilohertz. We need to convert that to hertz. So if I have 740 kilohertz, I want to convert that into hertz. My kilohertz go down here, and I know in 1 kilohertz I have 1,000 hertz. So there are my, that's my hertz for my frequency. And now we need to figure out our wavelength. So if we have the speed of light equals wavelength times frequency, if we're trying to figure out wavelength, then we're going to take wavelength equals speed of light over frequency. Plug our values in. So our speed of light is 3.00 times 10 to the 8th. That's going to be meters per second. Then we're going to put our hertz values in here. Remember, hertz equals 1/seconds. So when I put this in, my seconds are going to go on the opposite side. And what ends up happening then is we end up canceling out our seconds. That leaves our units in meters, and that's what our wavelength is going to get measured in. So if we put this in our calculators, we end up with 405 for our answer. So 405.4, and then it keeps going, is what comes up, but this can only be a 2 sig fig answer. So we would round this up. It would become 410 without a decimal, and that would be meters, and that would be your final answer then. Okay, so the next thing that we're going to talk about is the Beer-Lambert law. And the Beer-Lambert law then deals with putting kind of all of this stuff together, where we're going to deal with wavelengths and frequencies, and we're going to deal with intermolecular forces and all kinds of fun stuff. Oh, and our solutions and concentration. So when we look at this, what it says, it's used to relate the concentrations of colored solutions and visible light. And this is the formula. This actually appears on your formula sheet. A is absorbency. This is the molar absorbency. It is a constant. They would have to give you that in order for you to be able to solve this. You would not have to memorize those. And then the path length that it goes through, and then the concentration. So if we know all of these things, we can actually figure out the concentration of our material that we're working with. And so that's where the Beer-Lambert law comes into play, is that it's going to allow us to see or calculate what concentration of solution we're dealing with. And so that absorbency then, we have that at a fixed wavelength. So we're going to shine through light through, and then they will end up giving us, we'll be able to create a graph, and we're going to do a whole lab on this, and we'll create like a line graph. And then when you have an unknown, you have to be able to figure out where that belongs on that line based on the wavelength of light that comes through, and then you can backtrack and get the concentration. So you'll have a plot of absorbency against a wavelength, and then you end up being able to get a color for your unknown, and then from the unknown you're able to backtrack and get your concentration. So color wheel is kind of handy here because whatever is being absorbed isn't being transmitted and vice versa, so you can look at the color wheel and be able to figure out the complementary color on the other side. So theoretically, we're able to use this spectroscopy to with different wavelengths, and then we're able to perform experimentally and figure out the point of the highest absorbency. So we do that first, and then that's where we grab our concentrations after that. So it's kind of a cool lab. I take you step by step through it with a bunch of screenshots. So be prepared for that. And we will pick up here with our lab.